Today we are going to study about electric field due to non-conducting solid sphere. So what is the difference between a conducting sphere and a non-conducting sphere? So conducting sphere and non-conducting sphere. Non-conducting sphere. In a conducting sphere, charges reside only on the surface. That is, if we place a charge at an inside point, it will immediately come to the surface. For a conducting sphere, charges reside only on the surface. Therefore, it is similar to a charged shell. Therefore, it is similar to a charged shell. So, if in the question they ask electric field due to a conducting sphere, simply write that in a conducting sphere, charges reside only on the surface and it is similar to a charged shell, and then derive the electric field due to charged shell, which we have studied in the previous video. For a non-conducting sphere, if we place a charge at an inside point, it will stay at that point. That is, for a non-conducting sphere, charges can be anywhere within the volume. Charges can be anywhere within the volume. For a conducting sphere, charges will reside only on the surface, hence it is similar to a charged shell. For a non-conducting sphere, charges can be anywhere within the volume because it is non-conducting. So we will study about electric field due to a non-conducting solid sphere. A non-conducting solid sphere. For a non-conducting solid sphere, charges can be anywhere within the volume. So, case 1, electric field, electric field at an outside point, at an outside point. Suppose we have a non-conducting sphere like this, and we have charges inside the volume. For a shell, the charges will be only on the surface, but for a non-conducting sphere, charges will be inside the sphere. So we have a non-conducting sphere and we need to find the electric field at a point r distance from the center. So what we will do is that we will assume a Gaussian sphere in such a way that the point lies on the surface of the sphere. We will assume a Gaussian sphere in such a way that the point at which we need to find electric field lies on the surface. So we have a Gaussian surface or Gaussian sphere of radius small r. Capital R is the radius of the inner sphere or the inner non-conducting sphere. So we have Gauss law. Phi is equal to 1 by epsilon 0 times the net charge enclosed by the Gaussian surface. So what is the net charge enclosed by the Gaussian surface? The Gaussian surface is bigger than the non-conducting sphere. So the charges inside the sphere is the charge enclosed by the Gaussian surface. The entire charge contained in the non-conducting sphere is enclosed within the Gaussian sphere. In the case of shell, we define a new quantity called surface charge density, which is sigma equal to total charge divided by total area, because the charges reside only on the surface, not inside. But here we have charges inside the volume also. Therefore, we will define a new quantity called volume charge density, which is equal to total charge divided by total volume. So we can write rho is equal to total charge is Q. Let Q be the total charge contained in the sphere. Total charge divided by volume of the sphere. 4 by 3 pi capital R cube. So from this we can write Q enclosed is equal to, that is Q is equal to rho into 4 by 3 pi capital R cube, and we can substitute for this and we will get phi is equal to 1 by epsilon 0 rho into 4 by 3 pi capital R cube. This is the phi we got from the Gauss law. Now we have phi is equal to EA cos theta. Since it's a sphere, the area vector is outward normal and electric field is also in the outward direction. Hence, theta is equal to 0. Therefore, phi is equal to E into A. What is this A? This is the area of Gaussian surface. That is, this is the area through which the flux flows. This is the area of Gaussian surface. Therefore, area A is equal to 4 pi small r square. This is the area of Gaussian surface and the radius of the Gaussian sphere is small r. Therefore, area is equal to 4 pi r square, and we can write phi is equal to E into 4 pi r square. So we got two equations for phi. We have two equations for phi, and we will equate these to phi. So we have E into 4 pi r square, this thing, and we have phi is equal to 1 by epsilon 0 rho 4 by 3 pi capital R cube. We can cancel 4 pi, and we will get electric field E is equal to rho capital R cube divided by 3 epsilon 0 R square. So we got this electric field as E is equal to rho R cube divided by 3 epsilon 0 R square, and we have rho is equal to total charge per volume, that is equal to Q divided by 4 by 3 pi R cube. So we can substitute rho here. E is equal to Q divided by 4 by 3 pi R cube divided by 3 epsilon 0 R square. So we can cancel R cube, and we can cancel 3. Finally, we will get electric field E is equal to Q by 4 pi epsilon 0 R square. We will get electric field E as Q by 4 pi epsilon 0 R square, which is the which is similar to this electric field is similar to the electric field due to a point charge at a distance r. So what is the electric field due to a point charge at a distance r? This is E is equal to 1 by 4 pi epsilon 0 Q by r square. So we can say that electric field due to a non-conducting sphere, non-conducting solid sphere is equivalent to the electric field due to a point charge, electric field due to a point charge placed at the center, placed at the center. That is, from the center to the point we have the distance r, so we can say that electric field due to a point charge, we can say that suppose we have a point charge here q, what will be the electric field at this point? Electric field is equal to 1 by 4 pi epsilon 0 q by r square. This is the same electric field we will get if we have a solid non-conducting sphere of net charge q at this point. So that's it. Now we can move to the case 2, which is the electric field at the surface or electric field on the surface. So what we will do is that we will reduce the radius of this Gaussian surface in such a way that the point at which we need to find electric field lies on the surface of the Gaussian surface. That is, small r is equal to capital R. That is, we will make the Gaussian sphere coincide or exactly equal to the radius of the non-conducting sphere. That is, to find the electric field at the surface, we will simply replace r equal to r in these two equations. So we have electric field outside as rho capital R cube divided by 3 epsilon 0 r square. If we substitute r equal to r, we will get E surface, which is equal to rho r cube divided by 3 epsilon 0 r square, that is equal to rho r divided by 3 epsilon 0. Electric field at the surface is equal to rho r by 3 epsilon 0. Yes. And we have one more equation. This thing, in this equation, if we substitute E capital R equal to small r, we will get, we have E outside is equal to 1 by 4 pi epsilon 0 q by r square. We will substitute r equal to r. We will get E surface, that is equal to 1 by 4 pi epsilon 0 q by capital R square. So this is the electric field at the surface of the non-conducting sphere. So now we can move on to electric field inside the sphere. Case 3, electric field inside solid non-conducting sphere. Electric field inside solid non-conducting sphere. Suppose we have a solid non-conducting sphere like this, and we need to find the electric field inside the point. So we have a non-conducting sphere and we have charges inside the sphere, and we need to find electric field at an inside point which is at a distance smaller from the center. So what we will do is that we will assume a Gaussian sphere in such a way that the point at which we need to find electric field lies on the surface of the sphere. So we will draw this Gaussian surface like this, and we have the radius of the non-conducting sphere capital R. We can write phi is equal to 1 by epsilon 0 q enclosed, which is the Gauss law, and this is the net charge enclosed in the Gaussian sphere. We have rho as the volume charge density, which is the total charge per unit volume. This is the total charge per unit volume of the sphere. So if we want to find the total charge enclosed in the Gaussian surface, or if we want to find the total charge enclosed in the smaller sphere of radius r, we will multiply this value with the volume of that sphere, right? So rho is the charge per unit volume, and if we want to find the total charge in this volume, we will multiply this quantity with the volume. So the Q enclosed is equal to Q by, we can cancel 4 by 3, 4 by 3. We will get Q small r cube divided by capital R cube, and we can write phi is equal to 1 by epsilon 0 q small r cube divided by capital R cube. So this is the flux we got from Gauss law, and we also have equation for flux. Phi is equal to Ea cos theta. Theta is equal to 0 here, and phi equal to Ea. So what is this A here? Here the A is the area of Gaussian surface, which is equal to E into 4 pi r square. So we have the expression for phi. Phi is equal to Ea. We have phi is equal to E into 4 pi r square. We have phi is equal to 1 by epsilon 0 q r cube by r cube. Now we will equate these two equations. E into 4 pi r square is equal to 1 by epsilon 0 q r square by r cube. So we can cancel, sorry, it is r cube. So we can cancel r square and r square here. So we will get electric field inside as E is equal to 1 by 4 pi epsilon 0 qr divided by r cube. So we will get electric field as E is equal to 1 by 4 pi epsilon 0 q small r by capital R cube, and in terms of rho, if we substitute for q, we have here q is equal to rho into 4 by 3 pi r cube. If we substitute that value here, we will get electric field inside is equal to rho r by 3 epsilon 0. So this is the electric field due to a non-conducting solid sphere at an inside point R.